The beginning of space and time. The universe is vast and mysterious. When we gaze up at the night sky, we see countless stars and wonder about our place in this grand cosmic tapestry. Cosmology, the study of the universe, offers profound insights. We now know that the universe has a beginning. It is a dynamic entity, constantly evolving. We will explore the origins of the universe, from the Big Bang to the formation of galaxies, stars, and planets. The Big Bang model is supported by a wealth of observational evidence. One key piece of evidence is the cosmic microwave background radiation. This faint afterglow of the Big Bang permeates all of space. Think of it as a baby picture of the cosmos. Another piece of evidence is the abundance of light elements. Hydrogen and helium, the lightest elements, were forged in the intense heat of the Big Bang. Their observed abundances in the universe match the predictions of the Big Bang model with remarkable accuracy. The Big Bang was not a single event. It marked the beginning of a process. In the first fraction of a second, the universe underwent a period of rapid expansion known as inflation. During inflation, the universe expanded at an exponential rate. This rapid expansion smoothed out any initial irregularities. After inflation, the universe continued to expand and cool. Elementary particles such as quarks and electrons condensed out of the primordial soup. Within this chaos, the seeds of structure were being sown. As the universe continued to cool, protons and neutrons, the building blocks of atomic nuclei, formed. These protons and neutrons, influenced by the strong nuclear force, combined to create the first atomic nuclei. This process, known as Big Bang nucleosynthesis, occurred within the first few minutes after the Big Bang. The early universe was a hot and dense plasma. Light could not travel freely through this plasma. However, as the universe expanded and cooled, a crucial transition occurred. Electrons combined with atomic nuclei to form neutral atoms. This marked the end of the plasma era and the beginning of the era of atoms. With the formation of neutral atoms, the universe became transparent to light. The cosmic microwave background radiation, which had been trapped within the plasma, was finally free to stream across the cosmos. This radiation provides a snapshot of the universe, as it was just 380,000 years after the Big Bang. Gravity was at work, pulling matter together, setting the stage for the next chapter in the universe's evolution. The cosmic dark ages were not completely dark. The faint afterglow of the Big Bang, the cosmic microwave background radiation, still bathed the universe in a dim light. However, with no stars yet formed, there were no other sources of light to illuminate the cosmos. Gravity is a fundamental force in the universe. During the cosmic dark ages, gravity began to pull together the vast clouds of hydrogen and helium gas that filled the universe. These clouds, known as protogalaxies, were the seeds of future galaxies. Within these protogalaxies, smaller clumps of gas began to collapse under their own gravity. As these clumps contracted, they heated up. Eventually, the conditions became so extreme that nuclear fusion ignited. The first stars were born, marking a turning point in the evolution of the universe. Let there be light, the epoch of reionization. The first stars, blazing with intense ultraviolet radiation, began to ionize the surrounding neutral hydrogen gas. Ionization is the process of stripping electrons from atoms, turning them back into ions. This marked the beginning of the epoch of reionization. It was a gradual process. It took hundreds of millions of years for the radiation from the first stars to fully ionize the intergalactic medium. As more and more stars formed, the universe gradually transitioned from a state of darkness to a state of light. The radiation from these early stars had a profound impact on the universe. It heated up the intergalactic medium, preventing it from collapsing to form more stars. This helped to regulate the rate of star formation in the early universe. Astronomers are using a variety of telescopes to study this period in the universe's history. These observations are helping us to understand how the universe transitioned from the Dark Ages to the starlit cosmos we see today. The formation of stars, celestial furnaces, ignite. Stars are the fundamental building blocks of galaxies. They are cosmic engines that produce light and heat through nuclear fusion. Stars form within giant clouds of gas and dust, known as molecular clouds. These clouds are cold and dense, providing the ideal conditions for gravity to overcome gas pressure and cause the cloud to collapse. As the cloud collapses, it fragments into smaller clumps, each of which can potentially form a star. As a clump of gas collapses, it heats up. The temperature and pressure at its core continue to rise until they reach a critical threshold. At this point, nuclear fusion ignites. Hydrogen atoms fuse together to form helium, releasing an enormous amount of energy in the process. This energy creates an outward pressure that balances the inward pull of gravity. Stars come in a variety of sizes, masses, and temperatures. The most massive stars are extremely luminous but have relatively short lifespans, ending their lives in spectacular supernova explosions. Galaxies assemble. Islands in the cosmic ocean. Galaxies are vast collections of stars, gas, dust, and dark matter, bound together by gravity. They are the largest structures in the universe that are held together by their own gravity. Galaxies come in a variety of shapes and sizes, from spiral galaxies like our own Milky Way to elliptical galaxies and irregular galaxies. The formation of galaxies is a complex process that is still not fully understood. However, astronomers believe that galaxies formed from the gravitational collapse of vast clouds of gas and dark matter in the early universe. These clouds, known as protogalaxies, were much larger than present-day galaxies. As these protogalaxies collapsed, they fragmented into smaller clumps. Within these clumps, stars began to form. Over billions of years, galaxies evolve and interact with each other. Our own Milky Way galaxy is on a collision course with the Andromeda Galaxy, set to merge in about 4 billion years. The dance of gravity. Black holes and their influence. Black holes are among the most enigmatic objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. Black holes form when massive stars collapse at the end of their lives. They can also form through the mergers of smaller black holes. Black holes are invisible to telescopes that detect light. However, astronomers can infer their presence by observing their effects on surrounding matter. As matter falls into a black hole, it heats up and emits intense radiation. This radiation can be detected by telescopes. Supermassive black holes, millions or even billions of times the mass of our Sun, are found at the centers of most galaxies. These black holes can influence star formation in their host galaxies. They are responsible for some of the most energetic events in the universe, such as quasars and gamma-ray bursts. Cosmic evolution, a universe in motion. The universe is not static, it is constantly evolving, driven by the relentless forces of gravity, nuclear fusion, and the expansion of space-time itself. From the Big Bang to the present day, the universe has undergone a series of remarkable transformations. The early universe was a hot, dense soup of elementary particles. As it expanded and cooled, protons and neutrons combined to form the first atomic nuclei. Electrons eventually joined these nuclei, forming neutral atoms and making the universe transparent to light. Gravity then took over, pulling together vast clouds of gas and dark matter to form the first stars and galaxies. Stars lived and died, enriching the universe with heavier elements that would eventually form planets and life. The expansion of the universe is accelerating, driven by a mysterious force known as dark energy. Our place in the cosmos, awe and humility. The study of the universe's origins fills us with a sense of awe and humility. We are part of something much larger than ourselves, a vast and ancient cosmos that has been evolving for billions of years. We have come a long way in our understanding of the universe. From the first observations of the night sky to the latest space telescopes, we have made remarkable progress in unraveling the mysteries of the cosmos. Yet there is still so much that we don't know. The search for our cosmic origins is a journey of discovery. As we continue to explore, we are filled with a sense of wonder and excitement for what we might discover next. By studying the universe, we gain a deeper appreciation for our own existence and our place in the grand scheme of things.